Now, physical system that moves with SHM. So there are different systems which are moving with SHM. That is, we will find that in these systems, there are certain particles or the various types of things which are executing SHM. Like first is the torsional oscillator, and torsional means angular SHM. In this one, there is a wire and there is a disc, and the moment of inertia of disc is I, and we find that C is the couple. So we find that in the torsional oscillator, the disc moves in the circle about the axis, and when it moves about the axis, to complete one rotation, the time taken is t. So for one rotation, time is t, that is the time period, and it is calculated by formula t is equal to 2 pi under root I over c. So here we have not to deduce the formula, rather we have to use it in the numerical problem. So we should remember that in case of torsional oscillator means which is moving about the axis in rotatory motion. So t is equal to 2 pi under root I over c. So c is neta pi r to the power 4 divided by 2l, where neta stands for the modulus of velocity of the wire, r is the radius of wire. So radius of wire can be written as diameter by 2. L is the length of the wire, and I is moment of inertia of the disc. So when we say moment of inertia of the disc, moment of inertia is normally given by formula mr square, where r is the radius and m is the mass. Now we come towards the conical pendulum. In the case of conical pendulum, there is a thread of length L, and this thread is at a certain angle, and it is moving in circular motion about the dotted line, that is the axis. So angle between the dotted line, which is at 90 degrees to the plane with the string, is theta, and t is the tension in the string. So t is the time period. So t is equal to 2 pi under root L cos theta by g, where L is the length of string, theta is the angle which pendulum makes with perpendicular as shown in the figure, g is the gravitational acceleration or acceleration due to gravity. This acceleration due to gravity is different at different places. So if we consider conical pendulum at poles or at equators, we will find the value of g will begin to change, and as a result, we will find its time period will also change. Now we are coming towards the third case, that is the floating body. So we have taken a floating cylinder. So the green portion is just on the upper end of the water level, and some portion which is not shaded is dipped inside the water. So area of cross section of the floating cylinder is A is equal to pi r square, because its corners are in the form of circle. And in order to find its time period, we find that t is equal to 2 pi under root m over a rho g is the area of cross section, m is the mass, rho is the density, and g is acceleration due to gravity, acceleration due to gravity. Small m stands for the mass of the block, and area of cross section, as I have explained to you, it should be pi r square. Rho is the density of liquid in which the block is dipped, and t is equal to 2 pi under root LD over rho g, where L is the length of cylinder, D is the density, rho is the density of liquid, and g is acceleration due to gravity. And h stands for the length of the cylinder of cube inside the liquid when it is at rest. So it is nothing, it is length means its height. And now we come towards the case of U-tube. So there are two limbs in the U-tube, and we find that in both the limbs there is some water, and h is the height indicated from the ground. And we find that when one of the limb or some forces applied on one of the limb, the water gets displaced, and then we remove the force and water begins to oscillate in simple harmonic motion. So net displacement we have taken as 2x. So if we wanted to find the time period of the harmonic oscillation in U tube, it should be 2 pi under root L over 2G, where L is the length of the U tube and H is the height of the column from the ground level, and H is L over 2. Now we come towards the hemispherical shell. We find that there is a ball of radius r, that is small r. Small m is the mass of that ball and capital R is the radius of the hemispherical ball. So when the ball is allowed to move from one end, we find that the ball goes to the another extreme and it comes back to its original position, that is called one oscillation and time taken. To complete this one oscillation or one vibration in the hemispherical bowl, that is calculated by function 2 pi under root r into I plus I of the ball divided by mr square. But radius of the hemispherical shell or the bowl is much greater than r. So we assume that 1 plus I plus I ball divided by mr square is neglected. So we come to a formula 2 pi r over g, because small r is very small, or r is very largely much larger as compared to r. So it means that 1 I plus I ball divided by mr square, that is neglected, and the net formula will become 2 pi r over g. Now we come towards the oscillations of the piston in a gas chamber piston. So we are finding here there are two cylinders indicated, and in one of the cylinders the gas is fixed and a piston is in the stationary state, and the red portion is a ball inside a gas chamber. So oscillation of piston means that when the gas will be in motion, the red portion, that is the ball, will begin to oscillate about the mean position in the neck of the glass chamber, and x will be the displacement of that ball. So if it is displaced for one oscillation, the time taken will be t, and t will be calculated by formula t is equal to 2 pi under root Vm over a square m, where small m stands for the mass of the piston and capital M stands for the mass of gas inside the chamber. V is the volume of cylinder and M is the mass of piston. A is the area of cylindrical cylinder ball, and K is the bulk modulus of elasticity, which is given by delta P over delta V over V. That is change in pressure divided by change in volume over original volume. And for the first case, the isothermal process, the bulk modulus is equal to P, and in the adiabatic process, the K will be gamma P. You can remember from the previous knowledge that isothermal process or isothermal medium is that in which temperature remains constant and it obeys the Boyle's law. So in the adiabatic process, temperature is not constant. So we take K is equal to gamma P, and gamma is Cp over Cv. Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. That is what the meaning of gamma. So gamma is Cp over Cv, and the ratio is 1.41 for air. So adiabatic process is that in which temperature of the medium changes but heat of the system remains constant. So we find that K is equal to gamma P. Now, next is longitudinal oscillations of an elastic wire or the rubber string. When we use the term elastic wire or rubber string, we are taking into consideration Young's modulus of elasticity. And you can remember that Young's modulus of elasticity is the ratio of stress to the strain in that wire, whether it is made up of metal or rubber. So if we consider a rubber wire of rubber or a string, delta L will indicate the change in length, L1 is the original length. So if we wanted to find the time period of such a system, that should be 2 pi under root Lm over Ay. L stands for length of string, M stands for mass of ball, A is the area of cross section of the ball or area of cross section of the string, and Y is the Young's modulus. Now we come towards the eighth case of SHM, that is tunnel across the earth. Tunnel across the earth means across north and south pole. If we dig, there will be a tunnel, and if a particle whose uh, whose inertia factor is m or whose mass is m is allowed to move in the tunnel, and we will find when it will move in the tunnel, first of all it will be accelerated towards the center, and from center its velocity will be maximum, and it goes to the another side. The restoring force comes into action, and that will bring this mass towards the center again, and up to the time some external force is not applied to this mass, the mass will continuously execute SHM, and the time period of such an SHM will be given by function t is equal to 2 pi under root re over g, where pi and g are constant at that place, and r is the radius of the earth, which is found to be 6400 kilometers. The time of oscillation or vibration is about 84.6 minutes, as we have done earlier in calculations. Now we come towards the magnetic dipole in a magnetic field. When a magnet is suspended in a magnetic field, that is a uniform magnetic field, then we find that that magnetic field exerts force on the dipole, that is the magnet, and magnet begins to rotate about its axis. So the arrows, horizontal arrows, are indicating the magnetic field, and a dark line with which magnet is suspended is a thread, and the dotted line which is inclined at angle theta to the horizontal, that is the angle of twist. So time period of such a dipole is given by formula 2 pi I over mb, where m is magnetic moment, b is magnetic field intensity, and pi is constant. I is moment of inertia, and moment of couple is mb, that is the torsional constant. And another thing which is important is moment of inertia of a bar magnet. It should be calculated by L square plus B square over 12 multiplied mass of the magnet. So this formula not mentioned here, we don't require it, but otherwise we can remember that I will be taken as L square, that is the length of the magnet, L square plus that is L square plus B square, that is the breadth square, and divided by 12. L square plus B square by 12 into mass of the magnet. Now we come towards the electrical LC circuit, that is the inductance capacitor circuit, or that is a resonance circuit. So XL is equal to XC is the condition of resonance. So in the figure, the C is a capacitor, L is the inductor, and Q is the charge moving in the circuit. So for such a circuit, the time period, if we wanted to calculate, it should be 2 pi under root LC, where L is inductance and is calculated in Henry, where C is the capacitance, which is calculated in farads.